So far, we've been learning embeddings of words or whole sentences using tasks that aren't the one that we care about. What we care about is figuring out whether a movie review is a positive or negative one. What we've been predicting in order to train neural networks to generate embeddings is to fill in the blanks of sentences or guess the words around a word in a sentence. And those are different tasks, and therefore are capturing different notions of similarity than the one we care about most. The reason this often works, and why we've made so much progress on this classification task already, is that while similarity depends on the task, the similarity notion that you get by filling in gaps in a sentence is related to lots of different things that you might want to do later. Because in order to correctly fill in the blanks in text, you have to know what the text means. And so running this process gives you embeddings that do a good job of capturing the meaning of sentences and the meaning of words. So you have to know what opposite means and big means in order to fill in this blank. You also need to know a lot of facts about the world in order to properly fill in blanks in sentences. World knowledge is learned whenever you process a large collection of text and try to learn a model that fills in the blanks. So the biggest city in something is Toronto. You can't just know that Toronto is a city, you have to know it's a city in Canada. There's a notion that the same idea can be expressed in different ways, and that's a writing style. And in order to correctly fill in blanks in sentences, you have to have a model that's able to capture different notions of writing style. So that means that if you fill in this blank, big if true, you've captured a notion of how language gets used in these days. What's interesting is that even things like logic and math, which you might not relate to filling in blanks, actually shows up when you try to fill in the blanks. To fill in this blank, my big sister is 6 years older than me. When I was blank, she was 3 times my age. To figure out that answer is 2, you have to know something about how numbers work and solve a little bit of an arithmetic problem. So the result is that in order to complete this task, you need embeddings that capture a lot of different interesting facts about language and how it's used. And therefore, those embeddings are useful for lots of different classification tasks. But they're not the best possible embeddings for any given classification task because they capture a lot of different information, and you might want attributes that focus on the task that you care about most. How do you do that? Well, let me give you an example. Here's 3 movies: Star Wars: A New Hope, Spaceballs, which is a parody of Star Wars by Mel Brooks, and Robin Hood Men in Tights, another parody, not of Star Wars, but of Robin Hood, Prince of Thieves. So when you say which script should have the most similar embeddings to Spaceballs, you might think, well, Spaceballs is a lot about, Star Wars universe, so that should be the most similar. But then again, Spaceballs just makes a bunch of corny jokes, just like Robin Hood Men in Tights. So it's similar to both of them, but in different ways. The last step to maximizing performance of text classification is to provide the context of the task that you care about. If what you care about is figuring out which movies are most similar according to their genre, then we should focus on the fact that Spaceballs and Robin Hood just make jokes and do nothing else. If we care about whether the movie is about the space or the forest, then we should focus on the fact that Spaceballs and Star Wars are similar and that they're both about space. So it really depends on the classification task what you mean by most similar. Fine-tuning text embeddings allows us to come up with embeddings, or that is, a list of attributes, that focus on a particular aspect of similarity that reflects a particular set of labels provided in a training set. After learning embeddings by filling in blanks in text, like we've talked about, what you do is you continue learning those embeddings by predicting training set labels. This is a multi-step process where the first step about filling in blanks, which is called masked language modeling in the natural language processing field, learn some general a notion of an embedding of a sentence. And that general notion captures many different facets of language: world knowledge, how text is used, what it means, writing style, etc. But it's not necessarily the notion of similarity that you care about for your classification task. So after this pre-training phase, fine-tuning or post-training changes those text embeddings so that examples with the same label in your training set do indeed have similar attributes. And the way you do this is that instead of filling in blanks in sentences, you actually just train your neural network to predict the labels directly. So we've been talking about labels in the abstract. Let's focus back on movie reviews with positive and negative sentiment. The pre-training phase would use text about anything, not just about movies, in order to learn how language works, what all the words mean, all the world knowledge that's involved in interpreting language. And then the fine-tuning stage will only use the data that are movie reviews labeled with their positive or negative sentiment. So now we have a much smaller data set. And instead of trying to fill in blanks in that data set, we're trying to predict for each movie review whether it's a positive or negative one. So we're predicting labels instead of filling in blanks. We're doing it on the training set we care about instead of generic text data. And we're doing this to make sure that examples in the population from which our training set was drawn will have the property that two examples with the same label have similar attributes, a small distance, close by embeddings. One extra detail, not the most important, but you should know about it, is that when you fine-tune toward labels in a training set, you also create an embedding for the labels themselves, an embedding for positive movie reviews, an embedding for negative movie reviews. Therefore, the classification process becomes simpler. Before we had these embeddings for different labels, we had to make predictions by finding the k nearest neighbor examples, looking at their labels, and picking the one that got the most votes. But now, when we get a new example in, we can embed it and just figure out which label embedding is most similar, and we're done. And that makes things a little bit faster. So let's look at some code that carries this out. I think the important part here is not exactly what the code says, because that changes from year to year, but instead what it's trying to achieve, which is where the pre-training and fine-tuning and prediction is happening. So here we have a cell that picks out an existing model. This was already pre-trained. The masked language model, or fill-in-the-blanks task, was carried out on a very large collection of text data collected from all over the web, not just movie reviews, but everything else. We now initialize a model, and that model is going to take movie review text and movie review labels, those are the positive or negative classes, and perform additional optimization. This optimizer solves the problem of find the embeddings for sentences that do the best job possible of predicting the labels on the data that we give it. We get ready to train the model. This is the post-training or fine-tuning stage, because the pre-training stage happened already. Somebody else did it for us, and it was captured in this existing sentence transformer. We're going to go through the data 7 times. That's an arbitrary number, but it's a typical number for this kind of fine-tuning task. We'll go through all of our text, and in groups of 16 examples at a time, we're going to compute the loss, which is the error, how wrong the predictions are currently of predicting those labels from that text, and then have the optimizer improve the sentence embedding model in order to make better predictions. So this takes 25 seconds on my computer. We'll just fast forward. What we have now is a new embedding model. It's time to evaluate it. So we switch to the eval mode. We get the texts, and we're getting both the training and test texts because we need to embed them all. We're embedding the training set so that we can find nearest neighbors. We're embedding the test set so that we can know which nearest neighbors to look for in the training set. So what does this say? This says take the model and create an embedding for it. The details of why I did it this particular way aren't terribly important. But what's happening here is that it's going to generate attribute lists that are 384 numbers long for each movie review. And now that we have these new lists of attributes, we can make predictions. So we split the data into a training and a test set, and we use the same evaluate accuracy function for a 5 nearest neighbor classifier that we've been using all along. And when we run this, it doesn't take any longer than it did before, because it's a very similar process to what we already did with embeddings. We just have different embeddings. These embeddings were specifically tailored to notice similarity in whether something's positive or negative, instead of the details of writing style or factual accuracy or something like that. And we're up to 81% accuracy, better than anything we've seen so far. If, instead of using 5 nearest neighbors, we just took each test example embedding and compared it to our embeddings of positive review or negative review. That's a more typical way of using this model. So this just makes predictions directly. It's faster, and it's a little bit better in this case, but I think it could have been worse too. It's a similar performance, I would describe. So the k-nearest neighbor idea still works extremely well. It's just a question of how you're measuring similarity. And all this extra work of fine-tuning sentence embeddings is about making sure that the notion of similarity that we use is the one that reflects what we were trying to do in the first place. The labels in the training set, which tell us for each movie review, was it positive or negative? How would you get from 83% to 97%? Well, you'd use a bigger model in the first place that had more than 384 attributes and was trained on a whole lot more data. So that would take a little bit longer, but not terribly long. What does take a long time is building the original model, the pre-training phase, which you do once, regardless of which classification task you're going to perform. And then you fine-tune it for the task that you want to perform.